Welcome to The Explainer. Today we're going to tackle a really critical skill, one that comes way before you even think about algorithms or models, and that's how to truly know your data. Let's kick things off with a pretty powerful idea. A lot of people, they just rush into building models, right? Because that feels like the fancy, advanced part. But here's the thing. In real science, the most advanced skill isn't running the model. It's knowing if your data has even earned the right to be modeled in the first place. So that leads us to the big question, right? How do you actually know if your data is scientifically sound? And this is all about a fundamental mind shift, moving away from seeing data as just, a file on your computer, to seeing it as a real scientific object, something with a history, a context, and yeah, some very real limits. Okay, so what we're going to do is walk through a kind of pre-flight checklist. And this is a framework that honestly anyone can use, whether you're an undergrad just starting out in a lab course or you're a seasoned pro in the industry managing these massive data sets. This will help you really interrogate what's in front of you. All right, first up, section 1, data is not a file. Let's start right here because we have to completely reframe what data even means. It is so much more than just the rows and columns you see in a spreadsheet. Think about it. A number all by itself is, well, it's scientifically meaningless. Real, useful data is that recorded value, sure, but it's also the full context around it. We're talking units, the time it was collected, the location of the sample. It also includes the method used to get it, and, this is a big one, its known uncertainty. Things like detection limits or how noisy the instrument was. So take a look at this. Is this number useful? 7.2? What's so interesting here is just how completely ambiguous it is. Is that a pH level from a water sample? Is it a temperature in Celsius? Dissolved oxygen in milligrams per liter? Or maybe it's a performance score for some model. See, without that context, the value isn't just incomplete, it's totally unusable. And it can lead to errors that are off by a factor of 1,000 in your final conclusions. No joke. Okay, on to section 2, the pre-flight data checklist. So, let's imagine we found what looks like a really promising data set. Maybe it's on a public repository like Zenodo or Figshare. We're excited, we want to dive right in. But, hold on. How do we start our inspection before we get too carried away? Okay, before you even dream of downloading that file, there are 2 things you absolutely positively must do. Rule number 1, find and record the Digital Object Identifier, the DOI. Think of it as a permanent, unchangeable web address just for that dataset. It's the anchor that makes science reproducible. Rule number 2, check the license. This is what tells you if you are legally and ethically allowed to use it, change it, and build on it. And this is a perfect example of how the same rule can apply totally differently depending on who you are. So, for a student, a data set with a restrictive license, say a Creative Commons non-commercial license or a CC BY-NC, is probably fine for a class project. But for a data scientist working at a startup, that same license is a total non-starter. It completely blocks any path to building a commercial product. All right, now let's get to the heart of our audit. I want you to think of these 6 criteria as your scientific checkpoints. And look, the goal here isn't to find a perfect data set, because, spoiler alert, that pretty much never exists. What you're really doing is assessing the risk and understanding the limitations before you sink a single hour into actually analyzing it. Okay, moving on to section 3, spotting critical red flags. So if you ignore that checklist, you can run into some problems that will absolutely break your analysis. Let's take a look at what incomplete or just plain broken scientific data actually looks like out in the wild. Okay, you see this in a file. Nitrate, 50. 50 what? Is that 50 milligrams per liter as nitrate, or is it measured as nitrogen? Because depending on that one little detail, the actual concentration could be off by a factor of 4. Without units, the value isn't just messy, it's scientifically incomplete. This is a total failure of criterion number 1, documentation. Here's another one you might see, pH 15. Now, a pH of 15 is, well, it's physically impossible in a water-based solution. Your software, your code, it might just accept that number without a peep, but scientifically, that is a massive red flag. It tells you something might be seriously wrong with the quality control for the entire dataset, and that points to a big problem with its provenance. Ah, and this one's a classic. You see a missing value code like 9999. What does that even mean? Does it mean the instrument couldn't detect anything? Was the sample physically lost? Or is it something else entirely? The danger is, if your software reads this as a real number and throws it into an average or some other calculation, it's going to completely distort your analysis. It'll pull your averages way off and totally skew your results.
So this gets to a really crucial point. Some of the most dangerous errors don't even look like errors. Take censored observations. When a measurement says it's below the limit of detection, or LOD, the instrument is telling you it just can't reliably measure something not low. Now, the true value isn't 0, it's some small unknown amount. If you just replace it with 0, you're literally inventing a fact the instrument never gave you. The proper scientific way to handle this is to either remove those points or, even better, use statistical methods that are specifically designed for this censored kind of data.
All right, Section 4, building your feasibility map. So after you've gone through the audit, you've spotted the red flags, now you're finally ready to make what is probably the most important scientific judgment of all. You get to decide what your data can do and, maybe more importantly, what it cannot be used for. You see, the goal of an audit isn't just a simple thumbs up or thumbs down on a data set. It's to build what we call a feasibility map. You need to explicitly state, okay, given its strengths, this data can answer these questions, and, just as importantly, but given its limitations, these other analyses are absolutely forbidden. For instance, it's simple. If a dataset doesn't have a time variable, you just cannot use it for any kind of forecasting. Period. Let's make this super concrete. Imagine you download a dataset of chemical reactions from a bunch of published papers. It's chock full of successful experiments, right? Well, if you train a model on that, it might seem like it's performing great, but it will be completely useless for predicting failures in a real lab. Why? Because the dataset never ever showed it what failure looks like. That's a classic forbidden analysis, all because of selection bias.
So let's wrap it up with this. The big takeaway here is this. Before you start your next project, don't just ask what you can do with your data. Start by asking what its history, its context, and its limitations forbid you from doing. Taking that disciplined approach, well, that isn't just data prep. That right there is science.